Now we are going to start with the topic that is the vapor pressure for liquid solutions. Now what we will be doing in this, first of all we will be considering the liquid solutions. So what is liquid solution? As you all know that liquid solutions are those in which solvent is liquid. Solvent is liquid. So we are going to see the vapor pressure for the liquid solution, that is the solution which has the solvent as liquid. Now when we talk about the solute, so in this case what kind of solute we will be taking? We can take the solid solute, we can also take the liquid solute. So the solute can be liquid or solid, but definitely the solvent is going to be liquid. So we can have a solution with the solid solute and liquid solvent, or we can have a solution in which there is a liquid solvent and a liquid solute. Right. Now what we have seen till now, that suppose I have a pure solvent, let it be water. Now as you all know that water particles has tendency to escape, that means they have tendency to form vapor, right. So obviously there will be a vapor on the surface of this liquid and it will be exerting some vapor pressure on the surface of water. This is what we know actually, that again there is a water and water always has a tendency to get evaporate, and as it is a closed system, so vapors are not escaping outside, they get trapped on the upper surface, and when they get trapped on the upper surface they are somehow exerting a pressure, and the vapor that is called as vapor pressure. So what is the vapor pressure? It is the pressure which is exerted in equilibrium to the liquid by vapors. So this is what is the vapor pressure. Now, but here what we are talking about, it is a pure solvent. I will write here in order to just remove any confusion related to it. So we are talking about pure solvent. Now what happens when I add some solute into it? Definitely it is going to affect the vapor pressure. When I am going to add some solute, it is definitely going to affect the vapor pressure. Now if we talk about solute, so let us see that, let us take an example. Suppose I am adding a solute which is a volatile solute. What do you mean by volatile? Volatile means the solute or a substance which have tendency to get evaporate. Right. So I can have a volatile solute. As it has a tendency to get evaporate, so that means it will increase the vapor pressure, because some of that solute particles will also escape, like there is a solvent as vapors, but if there will be a solute present in it which is volatile, so obviously it is also going to escape, right. So it will also occupy the area above, so obviously it will exert some vapor pressure. So that means the vapor pressure of solute is just going to add into the vapor pressure of the solvent. So obviously we say that in that case there is an increase in the vapor pressure. Now I can add a solute whose nature is non-volatile, Non-volatile means that it do not have any tendency to get evaporated. That means it doesn't form any vapors. So if it doesn't form any vapors, so that means it is going to decrease the vapor pressure, as some of its molecules will occupy the surface and they will just offer the hindrance to the solvent particles to get evaporated. Right. So that means obviously they are going to decrease the vapor pressure of the solution. So this is what we can have. Again, as I have told you, pure solvent always have some vapors and it is exerting somehow some vapor pressure. And when we add some solute, depending upon its volatile nature or it is a non-volatile, it is going to affect the vapor pressure. So let us write few examples of volatile and non-volatile solute. Volatile, say petrol, diesel, kerosene, and non-volatile being sugar, salt, etc. They are non-volatile solute. Now we are going to study this vapor pressure, how this vapor pressure get affected, or what is the cause of vapor pressure, or what law that holds good for this vapor pressure. So before we start, so we are just starting with the Raoult's law. We have a law, very important law, that is the Raoult's law. Suppose we are considering here the solution liquid and liquid, that means liquid solvent, dissolvent liquid, solute, and both being volatile in nature. I'm just considering an example in which I have a liquid solute and liquid solvent, and if I talk about the nature, both are volatile. That means they have tendency to escape or they have tendency to form vapors. So obviously they are going to increase the vapor pressure, right? So see, what does Raoult's law actually states? Raoult's law states that partial vapor pressure of any component of solution is directly proportional to the mole fraction of that component in solution. So that means the pressure which is exerted by any component of the solution is just directly proportional to its mole fraction which is present in the solution. So let us explain with, let me explain you with figure. Suppose I have this solute. This solute is volatile in nature. This solute is volatile, and this law also holds for the volatile component, right? Because that is only going to exert the pressure. So suppose I have this, there is a solute which is a volatile. So obviously if there are solute particles here, so if we imagine that these are the vapors of the solute form, these are in the liquid form, these are just expressing in the liquid form solute, and this is just expressing their vapor form, right? So now what can I say? Let us say that the solute is considered as A, so its mole fraction, let us suppose as XA in the solution, and the pressure which it is exerting, because it is exerting alone, it is a partial pressure. Partial pressure is actually a pressure which a component would exert when it is present alone. So let us say its partial vapor pressure is P naught A. Now similarly, let's do it for the solvent. Suppose I have the solvent, again it has a tendency to get escape. So again it will be forming vapors. So I'll just put the dark circles. Right. So let us assume solvent to be B. Now this let the mole fraction be XB and the pressure due to this B component be PB, P naught B, partial pressure. Right. Now what actually this law states, now like for this law we need to make a solution. So let us make a solution first. So let this be a solution in which we are adding this and this. Both are volatile, and we know that their mole fraction is XA and XB, and their partial pressures are P naught A and P naught B. So let us mix these two solute and solvent in a container to form a solution. So that means what we'll get? We'll get the solvent, the solute particles, and as they are volatile, so they will be occupying some area above also, right? So let the pressure due to this is, we consider it as A, so let the pressure due to it is P1 and their mole fraction is XA, right? Now we have the solvent and it is also volatile, it also has a tendency to escape. So let us make it with dark circles. So they also have the tendency to escape, so that means they are also present in the vapor form. Let us say this component, the mole fraction of this solvent is XB and the pressure due to it is P2. Now what does this Raoult law actually want to say? It states that the vapor pressure of any volatile component, whether we consider solute or whether we consider solvent. So the partial vapor pressure of any volatile component is just directly proportional to the mole fraction of that component. So that means the pressure which is exerted, pressure which a gas would exert is directly proportional to the mole fraction. Suppose I need to find the pressure due to solute, so it is going to be directly proportional to the XA. Likewise, if I need to find the pressure, vapor pressure to PB in a solution, it is directly proportional to the mole fraction of this XB. To get the appropriate result, what we do, I'm just going to write it here, two equations here, right. So that means PA, if I remove the proportionality sign in order to make the calculations more, you can say the perfect one, what we do, we put the partial pressure of this into XA. So this is the pressure, this is what the Raoult law actually meant. And similarly for PB, so the pressure for PB is equal to the partial pressure of PB when it is present alone into mole fraction of this. So if I consider the total pressure which is obtained in the solution, so obviously it is going to be P is equal to the P1 factor plus P2 factor. And we know that I can just use it as P1 and P2 also, or A and B. So that means total pressure is equal to P naught A into XA plus P naught B into XB. So this is the expression by which we calculate the total pressure exerted by two volatile components, that is the solute and solvent, when they are present in the solution form. So this is what. And you know that I can also express this P total in you can say in a mole fraction of one component also. So let us see how. So I'll be just using this equation again. So I have Pt is equal to P naught A. As we know that it is a binary solution with the A and B component, we know that mole fraction in case of binary solution, sum of mole fraction is equal to of two component is equal to 1. So I can express the concentration of A in the terms of B also. So let us say XA is equal to 1 minus XB. This is what I am going to put here. This is what I am going to put here, because I am going to express the total partial pressure, or you can say I am just going to relate the total pressure in terms of molar concentration of one component, right. So what do I get? I get X1 minus XB, because instead of this I am writing this value P naught B into XB. I can also write in this way that P naught A plus XB taken as common, P naught A minus P naught. So this is what I can have the total pressure, and here what I am doing, here I am just trying to express the total pressure or relate the total pressure to the mole fraction of any one component. As I did for XB, you can also take the value for XA. So what conclusion actually you get from this thing? We get the conclusion, first is that vapor pressure of solution, total vapor pressure of solution can be related to mole fraction, right. And the second thing is that the partial pressure of any component is directly proportional to the mole fraction, or you can say that the total vapor pressure of solution can vary linearly with mole fraction. That means suppose I have the vapor pressure of solution, I have the mole fraction, so it varies linearly. So I am just going to explain the graph with graphically. As you can see in this P naught A is going to be constant, this is constant, this is constant. So obviously total P is just related to the mole fraction. So we can say it is directly proportional to the mole fraction of any one of the components. So that means we made two conclusions. One is that the total vapor pressure of solution can be related to the mole fraction or can be expressed in terms of mole fraction. Second is that we can just relate the total pressure with the mole fraction of any one component. So this is what we get, and when we just try to explain it graphically, what do we get? So let us make here the graph, or this side. So what I have in this, so let us assume that we have two components 1 and 2, or A and B, whatever. So let us say that mole fraction of x1 is 1 and the second component is non-volatile, or it is not present. So we know that when it is not present, so obviously the vapor pressure is just going to be due to this x1. So let us say that partial vapor pressure is P naught A for x1. Now similarly what we consider x1 as 0, that means this is not present, or it is non-volatile, then x2 is present and its mole fraction is 1. So obviously the partial pressure of this is going to be due to this, let us say it is P naught B. So this is how it varies, and when they are present in solution, so this actually line gives us the total P, that is the P1 plus P2, which is just equal to this P naught A into XA plus P naught B into XB. Now as you can see, suppose now I am just decreasing the mole fraction of x1. So let us say that I am decreasing the mole fraction of x1, and as we decrease we see that there is a decrease in the partial pressure of A also, because there is no mole fraction left. So we know that the partial pressure is only due to the mole fraction, and when the mole fraction is approaching 0, so that means pressure is falling down. And likewise, I am just decreasing the mole fraction of the second component, we see that it also decreases. So it specifies PA and it specifies PP. So this is what I am trying to explain you, that this is actually a Raoult's law, that it states that the partial vapor pressure of any volatile component in solution is just directly proportional to the mole fraction of that component. As we saw that this is the expression we need to calculate when two components are volatile, liquid solute volatile, and again the liquid solvent as volatile. And this is what we did to express the concentration in terms of any one component. So that means we can relate the total pressure with the mole fraction of the any one component. And when we talk graphically, we plot this graph as this, right. So this is what is the vapor pressure for liquid solution, and it is a Raoult's law. Now we will be just calculating the concentration in the vapor phase. So let's just look at the board carefully.